In this video, we're going to be learning about momentum, and we'll be doing some AP style practice problems with it. The first thing you need to know is that momentum, which is denoted by a P, is a vector, and it equals the product of an object's mass times its velocity. And that makes sense. You might have heard references such as that person has a lot of momentum because they're going really fast, or that car or that truck has a lot of momentum because it's really big. And that you can also get from this equation here. But where momentum is most useful is in the analysis of collisions. And that is because it is a conserved quantity. So that means that the sum of the initial momentum of all the objects in the system will equal the sum of the momenta of all of the objects after that collision. And the reason we don't use energy is because there are two types of collisions you need to know about. That is inelastic and elastic. So we've got energy and we've got momentum, and I'm just going to denote that as the vector P. In an inelastic collision, energy is not conserved. In an elastic collision, energy is conserved, and momentum is conserved in both of these within that system. Now, you might be like, conservation of energy is never destroyed. How can it not be conserved in an inelastic collision? And that's because we lose some energy to heat energy and sound energy in that collision. It's all still there, it's just not in a useful form. However, momentum will always be there. And also, you might notice it's a much simpler equation to work with than 1/2 mv squared, where you have that 1/2 and that v squared. So if you're dealing with an AP problem on the exam, or even on a test in your class, and you have a collision between two objects, always go to momentum. Here is our first problem. We have two objects, S and P, and we know they have the same momentum. So that means the momentum of S equals the momentum of P, hence MS Vs equals MP Vp. We want to know what would we have to do for our object P to have more kinetic energy than S. And we're looking at mass and speed. So we want 1/2 ms vs squared to be less than 1/2 mp vp squared. Now the key thing to look at here is the relationship between the m and the v variables. We see that in both of them the relationship to m is linear. However, in terms of kinetic energy, the relationship to our speed or our velocity squared is this squared here. And because that variable is squared, if we want object P to have more kinetic energy than S, then object P has to have a greater speed than S. Alright, in this problem we have a cart that has a mass of 2m with a given velocity v, and then it strikes a cart of 3m, which is at rest. The two carts are going to couple and move off together, and we want to determine what speed will they move off with. Alright, well, we need to use the conservation of momentum because we are dealing with a collision. So that means our initial momentum is going to equal our final momentum. Our initial momentum of our cart system, I should say cart, not car, is going to be the momentum of our first cart plus the momentum of our second cart, and that's going to equal the momentum of carts 1 and 2. This here is our initial momentum, that's our final momentum. So we know then m1v1 plus m2v2 is going to equal m1 plus m2 times this variable v. That is what we are solving for. Alright, so this is our M1, this is our V1, that is our M2, and that is our V2. We know V2 is at rest, therefore our second car has no momentum because it's not moving, it's not in motion. So there goes that term. Now we can solve for V to see that it equals M1 V1 divided by M1 plus M2. We know our M1 is 2M. We know our V1 is V. Divided by M1 plus M2, that is 2M plus 3M. That is 5M. Our M's cancel and we are left with 2V over 5. That is option B. Our last problem, we have a ball of mass M rebounding from a wall with the same speed we can see, and it also has the same angle. We want to know what is the change in momentum of the ball. Alright, first let's analyze the y direction. We have a change in momentum, and the y direction is going to be its final y momentum minus its initial y momentum. We can decompose these velocity vectors to see, we're going to call this V naught and V final. Here's our V naught y, here's our V naught x, here is our V final x, and here's our V final y. Notice that the velocity in the y direction is always upwards. It's always positive if we're considering positive upwards. So we know momentum is m times v, but the sine of theta is opposite over hypotenuse. We're looking in the y direction, so our velocity in the y direction is just our velocity times the sine of theta. So we can say we've got mv naught sine theta minus mv final sine of theta. However, these b's are the same. Our change in momentum in the y direction is just 0. So that means all of our change in momentum comes from the x direction, and hopefully you were able to see that. The direction of our vertical velocity arrows never changed, however, our arrows did flip in the horizontal direction. So our change in momentum in the x direction, that is going to be mv naught x times, or I should say mv naught cosine of theta. This is where our directions become critical. We're going to call into the wall positive. You should be able to derive this cosine theta yourself, especially from our sine example. Minus, we're coming out of the wall now, we are becoming negative, so minus a negative mv naught cosine theta. These become a plus. Our change in momentum in the x direction, and thus our total change in momentum is 2mv cosine theta. This should actually be a vf, but our speeds are the same. So that means option C is the answer. This 0 would come if you forgot about this sign change here. If you just said minus a positive, that would be incorrect. Anyway, hopefully you see how important it is really becoming for us to define these positive and negative directions. Here is the challenge problem for this video, and I really am going to encourage you all to challenge yourselves by not even looking at A, B, C, and D right now. I want you to just take a piece of paper, read the question, and write out what you think the answer is, and maybe a couple sentences justifying your answer. Oh, and the answer will be on my Instagram page shortly after the release of this video, and of course you can find it at the beginning of the next video.